of size greater than this particular matrix, which I'm claiming to be R cross R. If I choose R plus 1 cross R plus 1, that will have determinant 0, because that's what I've said. Order of largest square sub matrix of M for which determinant is non-zero. Got it? Okay, let me write down, then
Yes,
you will
sir.
understand. Let me write down. I think you have understood the first way of defining it. If someone says the matrix of rank of the matrix R, it simply means that at least one sub-matrix you can find out of order R cross R from the given matrix for which determinant is non-zero. That's the first condition. And the second is that every square sub-matrix of order greater than R will have determinant to be exactly 0.
Then
Got
why
it?
you said R plus 1 cross R plus 1 means it can be
I
R
am
plus
saying
2.
it can be R plus 2 also, R plus 3
Okay.
also.
Okay.
Every square matrix of greater than R.
Yes, sir. Yes, sir.
Okay.
Hmm.
Okay. So let me write all these things. So rank of a matrix R is a positive integer such that it satisfies following properties. First condition, that there exists at least one square submatrix of M of order R cross R such that its determinant is non-zero. It means I'm talking about the square sub matrix. Let me write this way, such that the determinant of um, this submatrix is non-zero. Okay, I should get at least one such square sub matrix. Second condition is every square submatrix of order greater than R, or why I was saying R plus 1, because you have already checking that is third cross 3 is 0, 4 cross 4 is 0. So when you are reached up to 2 cross 2, so you have find out that at least one of the 2 cross 2 is non-zero, and then you further check that 3 cross 3, every 3 cross 3 is 0 or not. So
Yes.
that's in the sense I was saying R plus 1. Otherwise greater than R, right? Every square sum matrix of order greater than R, you can say, has determinant equal to 0, right? So you can combine A and B, and as I said, we can write in one single statement if we want. The rank of a matrix R is equal to the order of the largest square submatrix, order of the largest square submatrix of M, for which we get a non-zero determinant. So this definition itself tells you that is, first of all, the largest square sub matrix. It means if you claim the matrix rank to be R, so R cross R is the largest square sub matrix for which you get the determinant non-zero. It means if you choose R plus 1, you will get determinant 0, or R plus 2, you will get determinant 0. Okay? Or R plus 3. for anything greater than R. So
Yes,
this
sir.
is sufficient in itself. So it combines both one or A or B, right? Clear? Now the rank is clear. Should I tell you some important results about the rank of a matrix, some important
Yes, sir.
properties? So few important results, things I would say about rank to remember. Is to remember. First is rank of a null matrix is always how much? Zero, right? Because every element is zero, so every element is it itself is a, it can be thought of as a square submatrix, and this will be the largest one. So it is zero basically, right? It is defined as zero. And the second one is rank of any non-zero matrix is, now if you have a non-zero matrix, so it will be rank will be always greater than equal to 1. It cannot be 0 because matrix is non-zero, it's not null. So the least possibility is rank is 1, otherwise maybe greater than equal to 1. Okay, fine.
Yes, sir.
Now if your matrix is a square matrix, that is important, and it is a non-singular matrix. Mind you, if it is a non-singular square matrix of order n, then its rank is always n. It's a very beautiful property. Rank of a non-singular square matrix of order n is n. If it is non-singular and a square matrix, then its order is n itself. If it is singular, then its rank will be less than n. Okay. Suppose now you have more than one matrices, two matrices suppose you have, and you take the product of two matrices. Then the property of the, related to rank says that rank of the product, that is suppose you have A and B two matrices, you take product of them, which is AB. So rank of AB can never exceed the rank of RA, I mean the rank of A and the rank of B individually, right? It means rank of AB will always be less than equal to minimum of rank of A and B. Got it?
Sir, can you repeat?
Yeah, I will repeat and I will write also. So what I'm saying is, suppose you have a matrix A whose rank is 3. Matrix B, suppose whose rank is 4. Okay, and you multiply it. So don't think that such matrix can be not be multiplied, because just by saying rank of A is 3 doesn't mean that the dimension of A is 3. Mind you,
Yes, sir.
dimension is different thing, rank is a different thing. And if a 4 cross 4 matrix can have rank as 3, right? Okay. So if rank of A is 3, rank of B is 4, suppose. So rank of AB can never exceed 3, which is the minimum of these two. Understood? It will
Yes,
be
sir.
always less than equal to 3. Either it will be less than 3 or it will be at max 3, which is the minimum of both A and B. You understand? That's A had 3, B had 4. If you multiply AB, the rank will be the always less than equal to the minimum rank of among A and B. Is it okay?
Yes,
Okay,
sir.
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 Yeah. So fourth properties, here's again important property. The rank of all these are kind of a theorems in mathematics. They are proof. So we are just writing without proof. Rank of product of two matrices can never exceed the rank of both the matrices individually. Okay. Or you can say that way, that rank of AB is always less than equal to minimum of RA, RB. Okay, where RA, RB are the ranks of A and B respectively. Okay, so it will always be less than equal to uh, minimum of RA. Fine, got it? Is
Yes,
that
sir.
okay? Okay. Now, another very important strong property about rank is that if you have a matrix A and if you take its transpose, then rank will remain same. Rank of A is same as rank of A transpose. That is very strong property. Okay.
Yes, sir.
Okay. Now another thing is, so another myth I should bust. If you think that rank can be calculated only for the square matrix, that is not true. I've never put any condition that the matrix should be square, right? Rank can be found out for any matrix, for any M cross N matrix in general, right? So rank of a matrix A, suppose of order M cross N. Suppose you have A matrix of order M cross N. I should write, let's suppose this way, N cross N. The rank R of A will be always, again, like we write, minimum of Mn, less than equal to minimum of Mn. It cannot exceed any of the you know dimension, number of rows or number of columns, whichever is minimum, it will be always less than equal to that. Okay.
Yes, sir.
So these are the properties you have to remember about the rank. First of all, rank of a null matrix is always 0. Rank of a non-zero matrix is always greater than equal to 1. Rank of a non-singular square matrix is n if the square matrix has dimension n, right? And rank of product of two matrices will always be less than the product of less than the rank of
Individual
the two
elements.
matrices individually, right? And the rank of A is same as A transpose, and rank of any matrix of order m cross n will be always less than equal to the minimum of mn. Fine. Okay, now this so far what is rank? We have defined what is rank, what are the properties of rank. Now how to find out rank? That's more important for us. So we are going to discuss in rest of the time how to find out. There are several ways, several method. First method is called enumeration method. So enumeration method is basically a method of observation. So like me first write down how to determine the rank. Or we can call any matrix by any name, A or M, whatever it is, right? So suppose so the first method I was saying is enumeration method. Enumeration. So this method is basically observational method, right? So these square submatrices that I was talking about earlier, you choose a square submatrix, right? These are also called as minors. They are also called as minors. So what you do is you evaluate all minors, you right, and based on that, you say that the rank is this. So for example, suppose I say this is rank, this is a matrix A, 1, 3, 2, some 2, 3, sub 6. Suppose this kind of some matrix is there. So it is 2 cross 3, right? First of all, its rank will be always less than equal to 2, right? That's for sure,
Yes, sir.
right?
Yes, sir.
Now for such a matrix, you can quickly see in your head that this is going to give me non-zero, right? So as soon as you get a non-zero value of 2 cross 2, so it rank cannot be less than 2 because we have already got a non-zero determinant for this.
Yes, sir.
Right? I told you the definition. So if you claim the rank to be, let's suppose 1, so I should get 2 cross 2. Every 2 cross 2 square submatrix has having determinant 0. Then we can say the rank is 1. But I've gotten, I'm simply by observation, I can see that its rank is its determinant is non-zero. This minor has determinant non-zero. It means its rank uh, cannot be less than 2. Right? That's for sure. Okay, and similarly, you choose here. You have already found. Now, if I now next thing is to check 3 cross 3 because for 2 cross 2 I have already found non-zero. So if I claim that the rank is 2, so I should get every 3 cross 3 or 4 cross 4 is determinant to be 0. Now there is no 3 cross 3 square submatrix possible in this. Okay, so therefore its maximum rank it can have is 2.
Sir,
Got it?
but there is no need to check for 3 cross 3 now because the rank should be less than equal to 2.
Yeah, to find. And otherwise, even if you try to check, then there is no 3 cross 3 possible, right?
Yes, sir.
So by observation, you can say the rank of A is 2. And you rightly said because we already know that rank can never exceed 2 in this case because 2 cross 3 minimum of 2 and 3 is 2. So rank anyway cannot go beyond 2. Okay, but right. So like this, what I'm trying to emphasize is that this method is based on observation, mental calculation, or by calculation doing on paper by calculating each and every minor and see the right. But this method will work only when the size of the given matrix is small, maybe 2 cross 3, maybe 3 cross 4, or something like that, 4 cross 5 at max. But suppose you have 10 cross 10 matrix, or 7 by 7, or 5 by 5, or maybe 5 by 6, like that. Okay, or 4 cross 6, or let's say 3 cross 4. So you will have several uh, minus to that has to be checked out, right? Because then minus will not be only of the order of 2 cross 2. They will be large in number, first of all, and not 2 cross 2. You'll have to see 3 cross 3 also, right?
Yes, sir.
For 3 cross 4 matrix, you can calculate the 3 cross 3 minus also, right? So your job is very tedious as you go, just you go above, 2 and 3 combination. If you have 3 or 4 combination, suppose I write any matrix, you understand what I'm trying to say. Suppose you have any matrix of 3 cross 4, suppose. So you have, let's say 1, 2, 3, 0, 1, 1, 3, 2, 4, 1, minus 1, 1, 0. Suppose this is 3 cross 4, right? So now you will have several 2 cross 2 possibilities, right? As well as 3 cross 3 possibilities, right?
Yes,
A
sir.
lot of work to do.
Yeah.
So you'll have to do all the determinants and do all this and that, right? So again, maybe you can do this for this one, but if size goes even further, 6 by 6, 7 by 7, or 7 by 8, 6 by 8, like that. Okay, so then you see your this method is not very friendly and convenient method to apply, right?
Yes, sir.
So there has to be some other method. So what is the other method? There are several other methods. So one of the method is called you apply the row operation in the matrices, and you reduce it to uh, a particular form, right? And that, what is that form? You try to make as many rows as possible as zero, right? You apply the row operation only in the matrices and try to convert the entire row as zero. I mean, you try to make all the elements of the rows zero, and you want to make more and more rows to be zero, right? When you are exhausted, and the number of rows left at the end which are non-zero will be the rank of the matrix.
That's a row equivalent form, I guess.
No, I will talk about the echelon
Oh,
form.
okay, okay.
Okay, so this is simply by the applying the row operations. So another method is, the second method is by applying row operations only. So suppose what you try to do is, let me write down. Uh, we apply the row operations. What do I mean by row operation? Row operations, I mean that you can add two row, you can subtract two row, you can multiply by any constant in the any of the row, and then subtract from other row, add some, like that, right? You can divide by some number like that. So these are called row operations, but you have to apply the operation only in the rows, not in the columns, right? You can apply the operation in the column also, but not mix the things. That is very important question. Apply, so best habit is to apply the operation in the rows only. Okay, don't mix it. In this method we don't mix. Later methods we will see that we can apply in both row and column all the operations, but in this operation we apply, in this method we apply the operations only on the rows, right? We apply the row operations only on the given matrix A to make all the entries of different rows to be zero, right? We want to make all the entries of, if possible, as many as rows, for as many as rows possible, to make the all entries of these all rows to be zero. Then after that, when you are exhausted, when you cannot make further the elements of the rows to be zero, then you stop and say that you count the number of non-zero rows, and that gives you the rank of the matrix.
Sir, in 0 rows, all elements would be 0.
Yes.
Or okay.
Yes, all 0. I will show you by example. Then you stop and say that you count the number.
Be 0.
Yes,
Or
and that gives you the rank of the matrix.
sir, in 0 rows, all elements would be 0.
Yes.
Or okay.
Yes, all 0. I will show you by example. Okay. For example, if I have a matrix A, which is 4 cross 4 matrix, I am choosing at random. So it may make life little difficult because the rank of a matrix is something that does in the calculation of the rank is something which doesn't have well defined in the sense identical steps. You can the steps can differ from person to person, but answer will not differ. Okay, if your steps are right. So what is the rank of this? Find out the rank of this matrix. So would you like to try, or should I tell you how to do by example? So find out rank of A for, by applying row operation only.
So can we also switch rows like R1, R2?
Yeah, you can switch, no problem.
So for that we have to put minus something or like
No, nothing.
Okay.
Just you can switch. Okay, let me solve one for you. That is so that you have an idea. So this is the this is the given matrix 1 2 3 0 2 4 3 2 3 2 1 3 and 6 8 7 5. So this has 4 rows. Determinant. If it is non-zero, then its rank will be 4 because it's square matrix. But if it is determinant is 0, then rank would be less than 4. So that's I'm leaving that thing to you check it whether it's determinant.
Yes, yes.
So 6 minus 6 is 0, 8 minus 8 is 0, 7 minus 7 is 0, 5. Yeah, the last one is 0, right? Is there any other way I can add or subtract or make the entire row 0? No, there is no other way. Because if I add first two and then R3 plus R3 minus R, so I will have non-zero values here, right? Similarly here and here. Even if I multiply with the 2 and subtract with this, I will have non-zero here, non-zero here, non-zero here. So I don't, it has to be singular matrix. Okay. Okay. 3. The rank of A is equal to number of non-zero rows is equal to 3. That is the answer. So it means since its ranks doesn't turn out to be 4, it means if you calculate its determinant, that should turn out to be 0. Right? That I can tell you just having the because of the rank property. It turn out to be 0. So it means since its ranks doesn't turn out to be 4, it means if you calculate its determinant, that should turn out to be 0. Right? That I can tell you just having the because of the rank property. If it determinant had not been 0, its rank would have been 4. Right? Because a square matrix. It has to be singular matrix. Okay. Okay. So this is again you will see for this particular example this was easy. I mean, but in some of the problems this A row operation method, it can be quite tedious, can be quite lengthy. You have to repeat the process several times and to make the row zero, and then you have to at the end will be always been a little bit doubt whether I can make any rows for the zero or not. You'll have to really devote good amount of time, right? So this also has some limitation that you can apply only operation along the rows, and sometimes it becomes very lengthy process, right? So there are other methods, a much stronger method than this. This is known as normal form. You reduce the matrix in the so-called normal form. What is the normal form? I will tell you. You reduce your matrix by applying row and column operations both, and you reduce them into the normal form, and then it's very easy to guess its rank, to guess the rank from the normal form, right? I will show you and tell you what is that. So let me first define that what's a normal form. Hope you are following, right?
Yes, sir.
If you are following, you can give me a thumbs up. So rank is possible order of squares of matrix of or the number of maximum possible matrices. Okay. So Jency had written some doubt. Matrix of 3 cross 3. So that's so rank is possible or reducing the matrix to the normal form, which you generally represent by n, normal form n. So normal form n is, what are the normal? There are 3 or 4 types of normal form. First is if you can reduce the given matrix by applying rows and column operation into some kind of identity matrix of some order, right? Suppose you have been given the matrix and you can apply rows and column operations, and you reduce it to identity matrix of suppose 3 cross 3 or 4 cross 4. Excuse me. If it is given 3 cross 3 matrix and you apply this kind, suppose I have 1 0 0 1 and I have this thing. So this matrix is the same. This and this are same form, because here I have IR to I2 basically, right? And this 0 means simply rest all the elements are 0, right? Depending upon what is the dimension of the matrices. Okay. It doesn't need to be square all the time. It could be something of this kind also.
Yes, sir.
This kind also. This is also the same matrix. You following? So this 0 simply means, these are symbolic, simply means rest all are 0, and you have been able to choose some I2. You have been able to convert the given matrix in this form where this is I2 and rest all are 0. So this rank of the given matrix will be 2 then. Are you following what I'm trying to say? Right?
Yes, sir.
Or you could have this kind of form. Again, this 0 is symbolic. IR is again some 2 cross 2 or 3 cross 3, whatever it is, or R cross R identity, right? So this this could be something of this kind. One, I'm taking the example, let's say this time 3 cross 3. And this. So this is nothing but this form, right? Okay.
Yes, sir. Sir, but why we are not representing it with IR and 0 only? Means in first matrix you have represented it IR 0 0 0 means
Because
3
it's
zeros.
yeah. So this particular one tells you that it can have 0 in the columns, you can have 0 in the rows as well. But this one is telling you that if you're chosen, suppose someone says that it is not necessary that I will always get this kind of structure. I can get this kind of structure. But I've just said in one or two. But I've just a normal form. So basically, you're into one of the above discussed normal forms by applying rows and column operations, R becomes the rank of the. Okay, clear?
Yes, sir.
Suppose, let's say, take an example to make the identity in the matrix and rest all element to be 0. So steps may differ from one person to person, but answer will never differ if consistency is there in the solution. If you have made committed any mistake, that's a different issue, right? So let's solve it, right? Because not too much time is left. So let me solve. So A is, so let me call of A to make the identity in the matrix, and well, I am a square matrix, and then add in R2 plus to R1, which is 0 here. Right? What should I get here? What will I get here? 2 2s are 4 and 4 4s are 8. Or less, you can put it if you wish, minus 1 by 8. Okay. C4, right? So what you get? 1 2 1 0 0 8 5 0 1 0 2 1. Fine. Okay.
Yes, sir.
All right. If I replace the C1 by C1 minus C4, so I get 1 0 and 0 here, right? I got 2 8 0 here. Okay, oh good. I got one more thing in my head. Zero zero one. Now you see the C2 column is becoming very interesting. If I divide C2 by 1 2, right? C2 by 2. So what do I get? 1 0 0 1 4 0. So what do you get? 1 5 2 0 0 1. Okay. And let me do one more thing. Okay, let me take this thing to next side. So like that you can go on and try to make, right? You can have your own steps. I'm just doing whatever it coming to my head. So I can do one more thing. I can subtract C. I can replace C3 minus twice of C4. So in that way, I will have 1 4 0, and I will have 1 5 and 0 here, right? And this is 0 0 1. Okay. Now do one more thing. Subtract C2 replaced by C2 minus C1, and also at the same time I will switch C3 and C4. So for this operation I will have C2 minus C1, which is 0 here, 4 here, 0 here, and I've already switched it with C3 C4. I have this sort of thing, right? Okay, now divide C2 by 1 by 4 C2. So I can see the identity is coming up here. 1 0 0 0 1 0 0 0 1 and 1 5 0. Okay, so let's do one more thing. C4 replaced by C4 minus C1 and then divide by 1 by 5. So what get 1 0 0 0 1 0 0 0 1. C4 minus C1 will give me 0 here, divide by 5 0 and 1 and 0, right?
Yes,
Okay.
sir.
And the last case, it is done now. What I can do, I can simply C4 minus C2, C4 replaced by C4 minus C2.
Yes, sir. It will become 0.
So 1 0 0 0 1 0 0 0 1, and this will be 0 0 0, right?
Yes,
That's
sir.
it. Now I cannot further do it because whatever I subtract or add 1 minus 1 will be generated. So I have been able to reduce this into which form?
Normal form.
Normal form. And this is the thing I've got at the final, and which is equivalent to IR0 form, right?
Yes, sir.
Where R is 3. So rank of the matrix is
3.
3. Like that.
Final form should be this one only. Either we do row or column.
Yeah, row or column.
Okay,
Final
fine.
form should be any one of these standard form which we
Oh,
discussed.
okay. Yeah.
Any of the form.
Yeah.
Okay, so your objective will remain to make it identity in the given matrix.
Yes, sir.
Right. So if it becomes 3 cross 3 or 2 cross 2, whatever it is, rest all the elements should be 0. Okay. So now next method is the row reduced echelon form or row echelon form, right?
Yes, sir.
So let's discuss this in the next class because almost time is done and that will require some understanding. I will have to explain what the echelon form is, right?
Yes,
Some
sir.
people call it the echelon form, some people call it echelon form. So I don't know what is the correct, because some people say that echelon is correct or some others say the echelon is correct. Maybe I will check on these days. We can check on AI what's the right pronunciation. Okay. So in my school, in my graduation, my teacher used to call it echelon form, but I heard some people call it echelon form.
Yes,
That's
in
why.
my university, they will call echelon.
Echelon form. So I
Yeah.
will check today what is the correct pronunciation. Okay. So that echelon form, or let's call it echelon for the time being, we will discuss in the next class because that's important concept in the rank of the matrix. So there is two row reduced echelon form or row echelon form, and based on that we can find it. That will be the second last topic, and after that very simple trivial discussion about linear equations that I was talking about, and then theory will be over. We'll do problems. So I think rank will still take the matrix will still take 2 lectures, next lectures, and 1 more lecture.
Sir, then what you will start after matrix?
I've not decided yet, but maybe Fourier series.
Oh, okay. Fine.
Okay.
Yes, sir.
Okay. All right. So see you in the
Okay.
next class.
Thank you, sir.
Yeah.
Good night.
Any doubt? Yeah, someone was saying
Sir,
something.
like how can we say like for rank equal to be 1, like only 1 cross 1 metric has to be formed, so it will
Yes.
be only an element then.
Yes. If you get one single element such that, and all the rest elements are 0, so rank will be 1.
Okay. Thanks, sir.
Okay. Good night. Bye.